Welcome back, everyone. The objective of this presentation is to introduce the concept of pipelining. If it were for us to run this processor as a single cycle processor, then the clock period would have to be as long as the longest timing path, which in the case of the RISC-V data path would be in the case of the load instruction operation or instruction, given by the summation of all the delays to read from the instruction memory, to read from the registers, to pass data through this multiplexer, and then have the ALU do its job, and then read from the data memory and pass through this multiplexer what we read from the data memory, and then write that back into the destination register. The idea of pipelining is to split this path into a number n of balanced partitions, then insert pipelining registers at these cutting lines, and clock the new design at a clock frequency that is n times faster than the initial clock frequency. Now, it is natural to do the partitioning to match the basic steps involved in the execution of an instruction. That is, instruction fetch, to fetch the instruction from the memory, instruction decode and reading from the registers file, execution, which in the case of the load instruction is an addition to calculate the memory address from where we want to read, and the fourth step, which is reading from the data memory, the data that we want to write in step number 5, write back the data into the destination register. So to implement pipelining, we need to insert at the partitioning or cutting lines these registers or pipelining registers, which will be clocked, all of them with a clock signal that will be much faster, n times faster than the original clock signal that we had for the single cycle data path. The way this pipeline data path will be operated is that instructions will be fetched and pushed into the pipe one after another. The first pipeline stage gets its output latched in this pipeline register, instruction fetch / instruction decode, that will provide at its output that information as input into the second pipeline stage, whose outputs will be latched by the second pipeline register, instruction decode / instruction execute, that will provide that information as input into the third pipeline stage, and so on, clock cycle after clock cycle. To illustrate that across multiple clock cycles, we usually use this type of a diagram where the x-axis shows time measured in clock cycles, and the y-axis shows the instructions that are fetched and executed one after another. This diagram is very helpful in illustrating how instructions undergo different steps through the pipeline. For example, the first instruction, load instruction, goes through instruction memory, reading from the instruction memory in the first clock cycle. It undergoes reading from the registers in the second clock cycle, and then it undergoes the ALU pipeline stage in the third clock cycle, reading from or writing into, well, in this case it's a load, so we read from the data memory in the fourth clock cycle, and the write back we write into the destination register and clock cycle number 5. At the same time, this type of a diagram is very helpful in showing at what stage of the pipeline a given instruction is or undergoes at a given time or clock cycle. For example, at clock cycle number 3, the first instruction undergoes the ALU pipeline stage. The second instruction, the subtract instruction, undergoes the register read pipeline stage, and the third instruction, the add instruction, undergoes instruction read and fetch from the instruction memory. So this diagram is helpful in illustrating that at clock cycle number 3 we have 3 instructions being worked on by the pipeline data path at the same time in parallel. This is what is called to refer to as the ILP, or instruction level parallelism. Now, in order to have the pipeline processor work correctly, we need correct control signals for the execution of each instruction through the pipeline, because the control signals are generated in the second pipeline stage. The trick is to generate and then carry them through the pipeline stages together with the data. For that, the pipeline registers need to be expanded to also latch and carry over these control signals, which are each consumed at the right pipeline stage later on. For example, the control signal that controls this multiplexer in the last pipeline stage is carried over from the moment when it's generated in the second pipeline stage through these pipeline stages as the clock signal goes on, and carries that to the final pipeline stage where it is consumed and will control this multiplexer correctly, so that the right information is being multiplexed and written back into the destination register as needed. So in summary, a couple of key points that should be taken home is that pipelining is a design technique to allow for multiple instructions to be executed at the same time. It is a perfect example of an instruction level parallelism, or ILP, design approach. Pipelining improves performance by increasing the throughput, that is the number of instructions that are being executed per unit of time. In other words, the pipeline executes multiple instructions at the same time, and it's good to remember, it's very important to remember that each instruction has the same latency, execution time taken in isolation. It's really the execution of multiple instructions that are being fetched one after another and pushed into the pipeline that will be executed at a faster pace that improves the throughput. There are a couple of challenges related to implementing pipelining, and those are related to a couple of different types of hazards that will lead to an increase in complexity of the design. These hazards include structural hazards, data hazards, and control hazards. Also important to remember that simple instruction set architectures like MIPS or RISC-V, the one that we studied this semester, makes pipelining easier or less complex. So that is it as a first introduction to the first concept of pipelining. On to the next topic in the next video.